Yeah, so am I audible?
Yes, sir.
Okay, so Pritam, yeah, so what is your question?
Sir, what is homomorphism?
Okay, so homomorphism is basically it's a linear transformation. Okay, it's another way of saying that a map is linear transformation. Yeah. Yeah, so yeah, maybe I guess in the lectures are somewhere wrote homomorphism instead of linear transformation, but they are basically the same thing.
Okay, sir. Uh, Sir, what is the dimension of a vector space with only the zero vector?
It's zero, right?
Yes, sir.
Yeah, so dimension is zero, right?
Dimension is zero, right? Okay.
Yeah,
Dimension.
because okay, so by convention, actually, the span of empty set is basically zero. Okay, so that's why. So okay, so it's basically it's a fact. Like we define that span is empty set is a linearly independent set. So and the span of empty set is basically zero vector. Okay,
But
and
sir, that is not an empty set, right?
sorry.
The set I'm talking about, that is not an empty set. It has the zero vector.
No. What I am saying, span of empty set is zero vector.
Span of empty set is
Set
zero
is
vector.
zero vector. Okay. So
Okay.
so empty set is basically a basis for your vector space. Okay, that's by definition. Okay. So since the cardinality of the empty set is zero, so
Yes, sir.
that's why the dimension of that vector space is zero.
Okay, sir.
Okay.
Okay, sir. And then I have few questions from the activity.
Okay. We'll take one by one. So I actually, okay, so what is your question? Like, is it from activity 6.1 or something?
Yes, sir. 6.1 and 2. One question from 2 and 3 from 6.1.
Okay, so what is actually, okay, so my plan was to actually give you some concept and take your question and solve. So what actually I thought, so I thought like I will explain some concept. Okay,
Yes, sir.
so I'll start from the first video 6.1. So I'll
Sir.
explain some concept, then I will take the question from 6.1. Okay,
Okay, sir. Okay,
and
sir.
then I will go to 6.2 and then I'll explain some concept and I'll start solving questions from activity 6.2.
Okay, sir.
So that was my plan, but yeah,
Okay,
so
sir. Okay, sir. We can follow then. And sir, will we have office hours?
office hours, it's like it's depend on your question. Like if you ask, like, so as you know, you should ask some question which is basically some conceptual doubt. So if you ask
Yes.
question from activity part, then obviously we are not going to take all this question in uh,
Okay, sir.
uh,
So I have asked an doubt which is conceptual, and I think it will require some time. So it would. I thought I was thinking that if we conduct an office hour, that would be better instead of solving it in such a session.
yeah. So I will suggest you post your question in that.
So I have posted it
Okay,
already.
so let me check and yeah, accordingly we'll plan. Okay,
Okay, sir.
okay, fine. Okay, so Krishna Mohan. So okay, so Krishna Mohan, are you here now?
Yes, I am there, sir.
So do you have any question, like some conceptual question from week 5 or some kind of activity question which you are struggling to solve?
Yeah, the linear mapping one. So I had some conceptual.
Okay, if certainly if you have conceptual doubt, then I'll suggest you to go and check the previous 2 live sessions. Okay, because they have done it explicitly. Okay, so uh, so if you have some conceptual doubt, then I'll suggest you go and check the previous live 2 live session actually. So if you
Previous
have
live
some,
sessions.
yeah, so they are actually they have discussed all these things. Okay,
So that's done.
so
The YouTube link is it? Is still active?
that is available. Like you can get it there. There is a playlist for maths too. Okay, so you can get it there. So So I guess some of your batchmate can give you the link, like it's available in YouTube. So that, I guess, if you have some conceptual doubt, then you can actually see these two videos. Okay. So
So
Yeah,
I'm
I'll
just
post.
looking at the playlist.
yeah, yeah.
So I just thought if I can have it, or from the calendar, I can check for the previous two.
I guess it's uh, maybe
Or
it's available in the YouTube. Like okay, it's fine. Like I guess it's in the portal. Okay, so if you go to the supplementary contents, so there you can get live session YouTube links. Okay, you can get it there.
supplementary contents.
Okay, so let me start with week so 6.1. So okay, so I'll start.
CP, it was on 31st Jan and 2nd February. So you can look it up in calendar.
Okay, okay. Jan 31st and Feb 2, YouTube calendar link will do the this one, right?
Yeah.
Okay, okay. Thank you very much.
Yeah.
Who was it actually? I just wanted to get the name. I didn't see it. Thanks anyway.
So yeah, so I'll start now. So okay, so the first thing I just want to tell you, like, how you can get the matrix representation of a linear transformation with respect to some ordered basis. So before that, let me tell you what is actually ordered basis. So it's more, so yeah, as okay. So yeah, so it's, as its name suggests, certainly it's a basis, but with some fixed order. So so suppose you have a vector space B. So B is a basis. So when I can say that B is a order basis. So first of all, B should be a basis plus some kind of agreement. So when I say this one, V1, V2, say the dimension of V is basically say n. So V1 up to Vn is our order basis. So as you can see here, V1 comes first. So this comes first, then this comes second, and this comes in the nth place. So you have a order. Okay. So if I take another basis, B dash, which is V1, not say V2, V1, V3, and Vn. So you can see, like, B and B dash, they are same, but as a basis. But B1, B2, they are not same as a ordered basis. As you can see here, B2 comes first. Okay, but here B1 comes first. Okay, so that's why, so the order of the elements in B and B dash are not same. Okay, so they are same as a basis, but they are not same as a ordered basis. Okay, so that's the difference. Okay, so that's the difference between basis and order basis. In order basis, the way the elements of the basis appears, it's actually it's matter. Okay. So for example, if I say this 1 0 and 0 1 and 0 1 and 1 0, they are same as a basis, but they are not same as a ordered basis. As so this comes first here, but here this comes second. Okay, so there is a difference between basis and order basis. So this part is clear, right?
But I have a question here. we can consider any order, right? Only thing is we should maintain the order in our consideration.
No, just like you have number of bases, so such as you can consider any order. It's not a problem. But yeah, when I'm talking about a matrix representation of a linear transformation, then you must have a fixed basis with a fixed order.
Correct.
Okay, for both
We
domain
can consider out of the two orders which you have written, we can consider the right side order also and work out on that basis.
Yeah. Just like, see, you have a basis. So as I said, it's a ordered basis and it's a ordered basis. So, but as a ordered basis, both are different. So it's up to you what you want to consider. Okay.
Right. Okay.
Okay. So the next thing is, so once I have an ordered basis, I want to use it to find a matrix representation of a linear transformation. Okay. So once I have an ordered basis, okay, I have written here. So once I have an ordered basis, I want to use these two order basis to compute a matrix representation of a linear transformation. So suppose I have a linear transformation T, which is from V to W, and say dimension of V is n, and dimension of W is n. So consider two ordered basis of V and W. Okay, so consider a basis. So I am considering this. Okay, so in some sense it's a abuse of notation, but so when I'm so basically ordered basis you should write in this way. So in this way it will be more clear to you that I'm following some order, because I am not writing in set form. I'm using open bracket, so you have some order. But okay, so as I said, it's a kind of abuse of notation. So I'm saying this is a ordered basis of V, and gamma is a ordered basis for
T.
W.
So why we are using it, like why we are using curly braces?
Okay, so as I said, like so the thing is, when you write 1 2, okay, so this is not same as 2 1, right?
Right.
Yeah, so it's better if you can use you can write like this. So when I'm writing like this, then it's saying that the order in which this element appears, actually it's matter. Okay. So
Okay.
but when actually I'm writing in the set format, so when I will write, so this and these two set are same, right? So here the order doesn't matter. Okay, but as I said, it's a kind of abuse of notation. Okay, so this is a ordered basis. Okay, let me mention it.
But sir, don't we have a concept known as ordered set?
Sorry?
Don't we have a concept known as ordered set?
Yeah. Ordered set concept.
We can consider this as an ordered set. Then we don't.
Yeah. That is also fine. Yeah.
Okay.
basically, when I'm writing like this, actually, yeah, I'm considering this as a ordered set. So this is a ordered basis. Beta is a ordered basis of V, and gamma is a ordered basis for W. So what I want to do now, I want to find the matrix representation of T with respect to these two bases. So what I will do now, so I'll take the image of the first element of the basis beta. So the first element is V1. So this is T of V1. So T is a map from V to W. So that means T V1 is basically in W, right? And I know this is a basis. This is a basis of W. So since it is a basis and it's a T V1 is an element of W, so I can write it as a linear combination of the elements of gamma. Okay, so I can write it as linear combination of the elements of gamma. So this is A11.
What are we discussing now?
Matrix representation of a linear transformation.
Oh, matrix representation of a linear transformation.
Yes.
Okay.
So this is A11. So the coefficient of W1. So as you can see, this A11 comes from this one and this one. So there is some meaning of this notation. Okay. So this is A21, A22, A omega 2, and similarly we can write A M1 omega M. So basically what I want to say that this coefficient, whatever coefficient I'm getting from this TV1 by writing, so what basically I'm writing TV1 as a linear combination of the elements of gamma. Okay, so when I'm writing this, I'm getting some scalar, okay, as a coefficient of the elements of gamma. So these scalars will give me the first column of the matrix. Okay. So they will give me the first column of the matrix.
Excuse me, sir.
Okay. Huh.
So we represented the first vector of one basis using the elements of the other basis.
Yes, as a linear combination of the elements of the your codomain.
Okay, sir.
Basis of the codomain.
But
So
why do we do this, sir? Is this like a rule, or is there like a reason we do this?
No, we are actually trying to find out the matrix representation of a linear transformation. So the thing is actually the matrix will give you a lot of information about the linear transformation. That's why we are doing it.
Okay, sir.
Yeah. So basically, in some sense, you can explicitly write the linear transformation using that matrix. Okay. So in some sense, it's so if you have the matrix representation in some ordered basis, then basically you have the linear transformation. Okay.
Sir, in the column space, why don't we write A11, W1? Like we only write scalars there.
Yeah, so that is how we define the matrix representation of a linear transformation.
So is that a rule? Like we have to exclude W1, W2?
Yeah. So that is the definition of a matrix representation of a linear transformation. This is a definition, right? I'm just telling you a definition, basically.
Okay.
Okay, sir. When in this linear transformation, we are using only basis, or can we use any other vectors?
No. You have to consider. See, you have these two information. You have a linear transformation and you have two ordered basis. Okay. So once you have these two things, then you can find out the matrix representation. Okay. So first, so you must have two ordered basis and you must have a linear transformation. Okay.
Okay, sir.
I have doubt here. So here you've written 1, 2, 3. I'm talking about what you wrote on right side. So that's represented as set, right? Because I was thinking the order, when you have the dimension of coordinates, you cannot change the order. So
Yeah.
Here it's 1, 2, 3 equal to 1, 3. Next, you are looking at from the.
No, sorry, it's not at all clear. Like your question, can you repeat it?
Yes, sir. Here, I was thinking like for the vector representation, order is important, right? The coordinates, whether the dimension is from V to W, projection of V on over W. So order is important, right? But 5, 1, 2, 3 equal to 2 and 3. How does it like equate to? How do these two equate to each other?
Which one?
1, 2, 3 and 3, 2, 2 and 3. So
no. Okay, so that's it. I was saying something. I was saying something different thing. Okay, you just for.
Okay.
So okay, so similarly you have tv2, and tv2 is in w. Okay, so similarly you can write tv2 as a linear combination of the elements of gamma. Okay, so then you can write as some linear combination of the elements of gamma. So this is 2 omega 2, and this is m2 omega n. So again, this color will give you the second column of the matrix. So this is A12, A22, AM2. Okay. And similarly, you keep on doing for all the vectors for this basis, you keep on doing. So similarly, if you do for TVN, so this is basically A1 omega 1 and AMN omega n. So this will give you the nth column of the matrix. So this is A11.
Sir, where we can
just a minute. Okay. So this is basically, so with respect to these two order bases, this is the matrix representation of the linear transformation T. Okay, so again, if you change the order basis, then you may get a different matrix representation. Okay, so the matrix representation is completely depend on these two order basis. Even if you change the order, like even if you change the order instead of so what basically, if you change the order, if you take V2, V1, V3, Vn, and say gamma 1, which is gamma 2, gamma 1, and gamma n. So for that also you may get some different matrix. Okay. So it's not like that you will get the same matrix. If you change the order, then you may get you will get a different base matrix. Okay. So is it clear how actually we are calculating the matrix representation of a linear transformation using two ordered bases? For
So please illustrate it with the example.
Sorry, sir.
Yeah.
Unable to understand
Obviously, I will give you example. But my question is whether this process is clear.
Yes, okay.
Okay.
this. Sorry, sir.
Sir,
No.
in the previous weeks, we had done vector space and we had solved some problems. Then why are we using a linear transformation and converting the vector space to another vector space?
So the same question I will ask you. When you have said, okay, so why you want to why you are studying functions? When you have sets, okay, you have bunch of sets, then why you want to study functions?
Because functions are useful.
Okay, then I can give you the same answer. Linear transformation are useful.
Yes.
Okay, so the main idea, okay, so okay, there is a big thing. Okay, so the thing is, when I'm in mathematics, when you have some object, so you want to study the nature of the object. Okay, so how?
Sir, is this related to optimization, sir?
No, okay, maybe see, linear algebra has a lot of applications. So I don't know whether what sort of use you can do. So what sort of work you can do in optimization using linear algebra, that certainly I don't know. But linear algebra has application in almost in every area. Okay, physics, chemistry, or maybe mathematics. Okay, biology, everywhere. Okay, so. But yeah, so one of the reason of studying this linear transformation is basically it will classify some class of vector spaces. Okay. So okay, so the thing is, as you know, like bijection, it's basically says that two linear transform. So two sets are basically as a set, they are basically same. Okay, because the cardinality is basically same. So when you have a linear transformation b to b dash, and when this t is basically isomorphism, so then v and v dash are more or less same. Okay, so if you want to study v dash, then you can study v, and if you want to study v, then you can also study v dash. Okay, so it's in some
Excuse
sense
me, sir.
giving you the class. Okay.
Excuse me, sir. Sir, are there any theorems for this linear transformation given in the lecture of last week, week 5?
Sorry?
Are there any theorems for this linear transformation which sir taught in the last week's lecture?
I don't know, like you should go and check the video lecture.
No, I checked, but the questions, I mean, there was no any theorem such as, but the questions in the graded are purely based on the theorems of linear transformation. And
Okay,
in
let me check.
Sir hasn't taught any.
No. Okay, so okay, that is your opinion, but yeah, let me check.
Yeah, but I checked this, so
yeah. So we'll check it.
Thank you.
Yeah.
So we were unable to solve these graded questions, and
I'll come to them.
Okay.
I think there was a session, open session on 31st January. There we will discuss about linear transformation.
Okay.
Yes.
So okay, so let me pick one question from activity 6.1. So let's say okay, so let me solve question number 1, option 1 and 2. Okay. Or maybe okay, there is only same thing. Okay, so T is a linear transformation from R2 to R2, and what is the definition of T? So what we want to do, we want to find the matrix representation of T with respect to the standard ordered basis, means with respect to this basis 1 0 0 1, and we are considering this basis as a basis for the domain. So here the domain is R square, and also for the codomain. Here codomain is also R square. So we are considering this basis for both domain and codomain. So what I will do now, I'll try to compute the value of this element. So this is now beta is 1 0 0 1. My gamma is also 1 0 0 1. Okay, so now what I'll do, I'll try to compute T of 1 0. What is T of 1 0?
1 0.
1 0. So then what I'll do now, I'll try to write this 1 0 as a linear combination of the elements of the gamma, right? So how you'll write?
1 into 1 0.
Yes, 1 into 1 0
plus 0 into 0 1.
Yeah, 0 into 0. So as I have said it earlier. So
why have you taken gamma here, beta and gamma?
This is an order basis for R2, the domain. Okay. This is a order basis for the codomain. Okay. So as I have said it earlier, so the coefficient of this gamma 1, gamma 2, and gamma m for this TV1 will give you the first column of the matrix. Okay. So here the coefficient is here 1. So this is a 1 1. This is a 2 1. Okay. So the first So the first column of my matrix is 1, 0, right? The next thing what I'll do, I'll try to compute T of 0, 1. So what is the value of T of 0, 1?
0,
0. So then how you can write 0, 0 as a linear combination of the elements of gamma?
0 times 1, 0 and 0 times 0, 1.
Exactly. So 0 times 1, 0 plus 0 times 0, 1. So this 0 and 0 will give me the second column of the matrix. So this is the matrix representation of T with respect to this beta and gamma. And here beta and gamma, they are basically same. So clear, like this, how actually we are computing. I'll do some more example, but this part is clear, right?
Yes, sir.
Yes, sir. So here beta and gamma should be same, right? Because domain and codomains
No. Actually, in the question, we have specified that for this question, beta and gamma are same. You can take some different basis. Okay. So okay, let me do it for this question. Okay. So if I'll take some different basis, then I will get a different. I may get a different
basis.
No, if I
matrix.
Yeah, matrix. If I'll take so they take beta. So beta may be say 2, 3, 4, 5. Okay, first you need to check that whether this is a basis or not. Okay, you can verify it quickly. Okay, this is actually probably it's a basis. Yeah. So this is a basis. This is an ordered basis, obviously ordered basis. So when I'm talking about matrix representation, then you can assume that in that case the basis is basically ordered basis. So this is an ordered basis for R square, and this R square is your domain. Okay. So I'll take another basis. Okay. So why I'm taking order basis? Then it will be easier for me to do the computation. But yeah. So
when we say ordered basis, we say with respect to another metric, another vector, right? Like beta is ordered
basis means, when I say ordered basis, means ordered basis. Okay, the order in which the element appears it's actually you have to keep track of the order of the elements in which they appear in the set. Okay, so
tell me the case where beta will be unordered.
No.
Yes.
We define domain and codomain. Different basis for domain and codomain.
Yeah, but I'm not understanding the concept of ordered, like the word ordered here.
What ordered?
This means if you
Had it
consider an
not
order,
been-
you cannot change the order. That's all.
Yeah, you can't write beta as 4,5, 2,3. Always, whenever you mention beta, it has to be 2,3, 4,5.
I guess you have joined little later, right?
5 minutes late, sir.
Yeah. So okay. So yeah, in the beginning, actually, I was discussing about the order basis. So the thing is ordered basis. Okay. So just quickly, I just want to.
If you could recall the first 10 minutes.
Sir, can we say that what we are defining as a basis is a linearly independent vector for domain, and what we are defining for codomain, they are the linearly independent vector for codomain.
Basis is vacuously linearly independent. Like how you can say that it's.
Sorry, sir. Dimension. No, what I am saying.
Okay, dimension certainly. See, the ordered basis as okay. I spent maybe 10-15 minutes on the same thing. Okay, the ordered basis is basically nothing. It's a basis. Okay, but the way I'm writing the elements of the basis is crucial. Okay, so so that's why you should try to join in the beginning.
No, sir. I am मैं समझ रहा हूँ सर, मतलब मैं एक्सप्रेस नहीं कर पा रहा हूँ अपनी बात को बस.
Okay, that is not true. So So the thing is, okay, so so suppose this is a basis. Okay, this is a basis for a vector space. This is a basis. So B is a vector space and dimension of B is 3. Okay, suppose this is a basis. Okay, and if I write B dash as B2, B3, so they are same, right? Whoever asked me about ordered basis, so can you tell me whether this beta and beta dash, they are same or not?
Yes, sir.
So they are same. Yeah, because both of them contains same elements. Okay, so as a basis they are same. They are same as a basis, but they are not same. But they are not same as a ordered basis.
Okay, sir. All right. Got it.
Why? Because as you can see here, V1 comes first, right?
Yes, sir.
Here V2 comes second. But in this case, V2 comes first, V1 comes. So the way the elements appear actually, so that is actually crucial in the case of ordered basis. Okay. So that is the difference between basis and ordered basis. Ordered basis is basically a basis with some extra conditions.
Yes, you are saying that this order should be as it is. You should not change it, right?
Yes. So as you can see, when I'm saying beta is ordered basis, so as you can see, always I'm computing T of 1, 0. That is the first element of the beta. Okay. And when I'm writing T of 1, 0 as a linear combination of the basis of the codomain, as you can see, I'm always writing 1, 0 first, then 0, 1 first, because here for gamma, this 1, 0 appears first, 0, 1 appears in second. Okay. Okay, so let me compute this. So my map is T of xy is, I guess, x0. So then, okay, then first I have to compute the image of this one, T of 2, 3. What is T of 2, 3? This is 2, 0. Yeah. So which I can write 2 in, as I have said, you have to consider first 1, 0, 2 into 1, 0 plus 0 into
0, 1.
0, 1. So then the first column of the matrix
2, 0.
2, 0. Similarly, if I take, say, what is my second element of the
4, 5.
4, 5. So this is 4, 0.
4, 0.
So then I'll get 4, 0, right?
4, 0.
Right.
4 times the same thing, 0 times the same thing. So this is the matrix representation of T with respect to this basis for the domain and this basis for the codomain. And here, as you can see, both the basis for domain and codomain are same. So this A, so here, this is the matrix representation of the linear transformation with respect to this basis for the domain, this one for the codomain. So as you can see here, in both the cases, we are getting two different matrices. Okay, so the matrix representation is completely depend on the ordered basis. Okay.
So, sir, this beta and gamma in the above example both have the same basis, and they are also ordered, right?
Yeah, ordered.
Not this, the previous one.
When I'm talking about matrix representation of linear transform, vacuously you take, okay, assume that always assume that the bases are the ordered basis. Okay. So because I cannot talk about matrix representation of a linear transformation for a non-ordered basis. Okay, that doesn't make any sense. Okay, so when I'm talking about matrix representation, that means I'm considering two ordered bases, one per domain, one per codomain. Okay, so which question you want me to solve next?
One question, sir, before that. So can we say that image is also known as column space?
I'm not talking about the image and kernel of the linear transform. Just concentrate on the matrix representation of the linear.
Okay, so
I'll come to that if, like, yeah.
So activity 6.1, question number 4.
Okay, for that I have to solve question number
3.
3 probably.
Yes.
So I think the answer is wrong.
Okay, certainly that is possible. Okay, I'm not denying that. Okay, let me check it.
Sir.
Okay, so let me start with Pritham with question number. You have doubt in 4. Let me start with question number 3. Okay, so T is isomorphism. Yeah,
sir, am I audible?
Yeah, you are audible. Pritham, I guess answer is correct. Okay, so.
Sir, what I am saying is, please discuss in this question how we can prove that this is 1, 1 or on 2. Because, sir, if it is given as a function, it is understandable.
That is okay. That is I'm going to. Okay, don't worry. I will discuss how we will prove it that it is 1, 1.
Okay, sir.
So yeah. So maybe before that, shall I recall the concept of 1, 1 onto of a linear transformation?
No, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir. And also, sir, please recall when we say that a matrix, it is a linear transformation when some expression is given.
Okay, that basically
means
already
that two conditions and
no, that actually I guess we have discussed 2 times. So that I guess you have to go and check the previous 2 live sessions, because again if I'll spend, then there is no point of repeating the same thing again and again. So yeah, so so I just okay, so W is a basis. Sorry, not W is a basis. W is a vector subspace of RQ.
Yes, the answer is correct. I did some mistake there.
Yeah. Because it's basically it's a map from dimension 2 to dimension 2. Okay, so
Yes, sir. Yes.
yeah. So it's basically we're writing 3 coordinates just to fool you. Yeah. So yeah.
Yes,
so
sir.
basically that is the thing. So it's 3 coordinates doesn't imply that it's the dimension is 3. It can be 2.
Yes, sir.
So this is a subspace that you should check. This is a subspace of R3. And one basis is given. So basis is given. Okay, so it's basically so okay, this basically tells you no. Okay, it's fine.
भाजो बाली चोरा है जाओ जल्दी जान कुछ हाँ वाणी.
Okay, so please mute yourself. Okay, so
मामा या
so beta is 210. Okay, so this is a basis of W. So and what is that? The next one is let T is a linear transformation. T is a linear transformation from W to R square such that T of 2, 1, 0
Equal to 1, 0.
1, 0. Another information is given. T of 1,
0,
0, 1 is basically 0, 1. So Okay, so what I want to find? I want to find a algebraic expression for t x y z. So I want to find a algebraic expression for this thing t of x y z. Okay, so so pick element. W, right? So this is basically same as, because by the definition 2 y plus z yz, right?
Yes, sir.
So this I can write 2y y 0 plus z 0 z, right? Fine. So this is same as y into 2 1 0 z into 1 0 1. Okay, so then if I apply t, both the sides, so what I will get? So t is a linear transformation, right? It should preserve the linearity. Okay, so if I apply t, what I should get? T of x y z
equal to y times 1 comma 0.
T into, yeah, T into T of y times T of 210 plus
0
z
plus
times T of
10 1 0.
1 0 1. So but it's given that T of 210 is what?
1 0.
1 0, right?
Yes, sir.
So okay, what I am doing? Okay. Y into 1 0 plus z into
0
0. So I should get yz, right? Right.
Sir, can
Yes, sir.
you go up a little bit? Can you scroll up?
Yeah, sure.
Yeah.
So what is your doubt here?
Here, okay, because this is defined, therefore we are.
Yes. Which one?
The xyz is defined as 2y plus z.
Yes. The condition is given there. Okay. And yeah, so basically once you replace, okay, the other one is basically it's if you replace, because x is 2y plus z, so then y is basically x minus y minus z, and z is basically x minus 2. So instead of yz, you can write x minus y minus z and x minus 2. So okay, so the question is, next question is whether t is 1 1 or not. Okay, so I got the expression for the linear transformation, right? So my expression, so t is w from R2, and remember that dimension of w is 3. Sorry, not 3. It's a subspace of R3. Okay, the dimension is 2. Okay. And the expression for this is yz, right? So for injectivity, what I have to show?
T of v equal to 0, then v equal.
For injectivity of a linear transformation, I have to show that T of
T of V is equal to 0
V equal to 0, then V equal to 0.
implies V is 0.
Yeah, so
Sorry,
it implies
right.
B is 0. Yeah, so that is also correct. Yeah, T of B is 0 implies B is 0. Okay, so
or sir, we can directly say na there is one independent variable, so the nullity is 1, and if the nullity is 1, then
no,
it
there are so
cannot
many
be an
things
index.
actually. There are so many things you can say. Okay, so okay, but yeah, so nullity. So my first question is where actually you are getting this independent variable, dependent variable here, like for a linear transformation.
Sir, actually the equation is given na sir. If we take x and y are the dependent variable, then z is independent. If any of the two, if sir, in the equation there are two dependent variable and one is independent, no?
Which one?
So the equation x is
domain.
equals to 2y plus z.
Hmm.
So there are two dependent variables and one independent variable.
When you will talk about the matrix, okay, when you will
Yes.
form a matrix, you have two independent variable and independent variable. So after that,
Yep.
yeah, so you have two independent variable, say maybe yeah, one dependent variable. So yeah, so you have that. So after that, what you can say?
So actually after forming the t, sir, after forming the t, the representation of t, sir, there are two dependent variables and one independent variable. So
No,
nullity is not
so
zero, na?
here basically nullity is
Not zero, na?
yeah. So basically, see so you are applying some concept of matrix solving for solving a system of linear equation in this direct in the linear transformation. So obviously you will get the wrong answer. Okay. So that certainly you cannot apply here.
Oh.
Actually, W is a subspace of R3 also. Therefore, you are reducing it to an R2 dimension.
Yeah. So okay, it's not the nullity is basically 0. Okay. So why the nullity is 0? Okay. So what I have to show? I have to show that T of B is 0 implies B is 0. So for that, what I have to show that T of XYZ is 0 0 implies these are basically the same thing, right?
Correct.
Yes, sir.
Correct.
Yeah. So what is okay? What is T of XYZ?
YZ.
So YZ. So T if T of, so I'm proving this implies this. So suppose T of XYZ is 0 0. That means YZ is 0 comma 0. That means Y equal to Z equal to 0. But you have another relation here, right? You have some relation in the coordinates of W.
X
Right.
equals to Y plus Z.
X equal to 2Y plus Z.
So that is also X is also 0.
So that means X equal to 2Y plus Z, which is also 0, because I have Y equal to 0, Z equal to 0, and I have a relation in between X and YZ, and using that I am getting X is also 0. So that means my X, Y and Z all are 0. So I'm done. Basically I proved that T of B is 0 implies B is 0. So then my map is, so T is 1. Yeah, T is 1, right?
Yes, sir.
Yeah.
Answer for on to, please discuss.
On to, okay, on to what is there in on to, like it's basically it's on to, right? Okay, so yeah, so let me quickly tell you, because okay, so on to so this, what is image of, so for onto-ness what you have to show?
For all
apart from V, we have another element that gives us 0.
What is the definition of onto? If T is
for all V in R square, there must exist W in small w in W such that T of W equals V.
The same definition. Okay, so basically you don't remember the definition onto when you can say that a function is onto. Okay, because there is no difference between the definition of ontoness of a function and ontoness of a linear transformation. Okay, they are basically the same thing. Okay, so let me
the codomain is equal to the range.
Yes, that is the thing. Okay, so okay, let me define. So if T is a map from V to W, then how you define image of T? Image of T is basically the set of all elements. So it's basically W in W such that there exists a V in V such that T of V is
W.
So basically what it's saying, so it is, this is your V, this is your W. So image of T is basically set of all elements of W which has a pre-image in V, means T takes V to W. Okay, so image of T is basically set of all elements of W which has a pre-image in V. Okay, so this is this image. This is the image of T, and as you can see, image of T is a subset of W, right?
Yes, sir.
So, but because of the property of linear transformation, you can say that it's not a subset, even it is more than a subset. Okay, it's a subspace of W.
Yes,
image
sir.
of T is a subspace. Image of T is a subspace of W. Okay. And once you have a subspace, once this is a subspace, you can talk about the dimension of that subspace, which is basically the rank of the linear transformation. Okay, so this is a subspace. This is a subspace. I guess rank is there in week 6.
Yes.
Okay, so once this is a subspace, so the rank of T is basically, by definition, it's a dimension of image of T. And if image of T is same as W, if image of T, so we know that image of T is a subspace of W, but we don't know whether it's a it's same as W or not. Okay, if image of T is same as W, then we say that T is
onto.
Okay, so once the image, as someone already said it, that once the image and codomain are same, you can say that linear map is onto. So now, can you say, like, can you tell whether this is so to show that this map is onto, what we need to show? To show that this map is onto, then what we have to show? I just gave you the definition.
For every y and z in the right side, there is always exist one element in the
basically what we have to show? We have to show that image of T is
R square.
Yeah. See, I have said that if image of T is W, then I can say that T is onto. Okay. So what is W here? W is the codomain, right? W is the codomain. So here, what is the codomain? It's R square. This is my codomain.
Yes.
If I can say, I can prove that image of T is R square, then my T is onto. So what is image of T?
Image of T is YZ. Yes.
Right. So what is this set?
This is R2.
Yeah.
So
that means T is onto, right?
Yes.
T is onto. Yes, sir.
Yeah. So T is 1, T is onto. Okay. So okay. So
Sir, may I ask
please.
one thing? Sir, image of T is subspace of W. I am not getting this.
So that you should try to prove image of T is a subspace of W. So do you agree that image of T is a subset of W?
Yes, sir.
Yeah, then try to prove it one by one, all the properties of subspaces. Okay. So when you can, so you go and check the definition of subspace. You check one by one. So basically, what we have to show to show that image of T, which is a subspace of W, what we have to it's closed under
Closed under addition
and closed under scalar
multiplex. Scalar multiplex.
That you need to. So one thing, yeah. So if
sir, actually I have a doubt. So if we have a matrix, transformation matrix, and if we do say row reduction, and if we find the rank of the transformation matrix to be equal to the original matrix and nullity 0, then it is both 1, 1 and on 2. Am I correct in understanding, sir?
Can you repeat?
Sir, let me give you a 2 cross 2 transformation matrix.
No. Suppose T is a linear. T is a linear transformation, and you have some matrix A.
Yes, sir. Let it be 2, 2. Let it be 1, 2, 3, 4.
1, 2, 3, 4.
Yes, sir. So in this matrix, if you have 1, 2, 3, 4, and for this we perform row reduction.
Yeah, you will get identity matrix.
Yes, sir. So if we do row reduction for
it will be 1.
Yes, sir. If we do row reduction for this particular thing, we get identity matrix whose rank is actually 2 and nullity is 0.
Yes, true.
So this is both 1, 1 and on 2.
On 2, yeah.
Correct now, sir. So
yes.
we can do row reduction for the transformation matrix and find it is 1, 1 on 2 also.
Yeah. That is what is there in your third lecture, right?
Yes, sir. Yes, sir. Yeah. I just had a doubt to confirm.
Yeah.
Sir, can you discuss the alternate methods of finding 1, 2 and 1 to 1 and on 2 here?
Yeah. That I will go one by one. Like.
So can you go with the question AQ9, AQ 5.5 for question number 9?
AQ 5.5.
Question number 9.
I'll discuss it later.
You can go with on to and this.
So can we make a matrix out of this question discussed here?
AQ 5.5, question number 9. Yeah, question number 9. You want to okay, like you whether I guess you.
I'm not able to get how it is onto.
No, that is fine. But I guess you. So have you checked the previous live session whether they have discussed this question? I suppose.
Okay.
Yes, you can check. Like it's basically a same concept. We can discuss it here, but you please go and check it. Like,
okay.
Otherwise, yeah.
Okay.
There is no point of repeating the same. Okay, so I was in matrix representation of a linear transformation. Okay, I'm done with that. Okay.
Here, can you discuss the alternate methods of 1 to 1 and
yeah, I'll come to that one by one because so as I'm following some
right.
Yeah.
So same activity, question number 6.
Question number 6.
Which 6.1?
Yes, sir.
Yeah, so okay, so let me discuss it.
Excuse me, sir. So can we make a matrix out of the question discussed here?
No, I have explained you 2 example, right?
No, sir, this question we can find the matrix also, no?
Yeah, you try to do it like the same procedure. You try
Yes,
to do
sir.
it. If you are facing problem, just let me know. You have to follow the same. There is nothing, some kind of tricky thing I'm using to find the matrix. See, if you can express those, see that the main part is this one. Okay, so the main part is this one, expressing t of 1 0 as a linear combination of this one. Okay, so if so here I'm taking some standard basis, or maybe my linear transformation is in a good form. So that's why as you can see here, I'm x0. So in this case, it's easy for me to compute the matrix representation. So if you have some complicated thing, then basically the main problem is to find this one. Okay, you have to, if you have some different basis, then the main difficult part is to compute this one as a linear combination of this one. Okay, that is the main part. Okay, once
Sir, I asked this question because beta is given but gamma is not given here, so that's why I asked this question.
Okay, if see
So
that
in the third question,
what, see, to find a matrix representation, you have to fix some basis for the domain, basis for the codomain. Okay, if it is not given here, you can take something. Okay, and you can start computing. Okay, if it is not given, so then you choose some basis for R2, some ordered basis for R2, and try to compute the matrix representation. Okay.
Okay,
sir. Can I ask question from week 2?
Not now. I'll take in the end. Okay. Okay. So yeah. So what is your doubt in question number 6?
So I have solved it in a way, but I was curious whether that is the only way or there is some other way to do it.
No, I didn't get your point. So can you tell me how you solved it?
So for example, can you see the question?
So you want me to share the question?
No. Is it visible to you?
Yeah, actually, I'm using some different system to.
Okay, sir. So for the first option, I observed that W equals U minus V.
3 1 0 U, V is 0 1 7, and W is 3 0 minus 7. Yeah.
Yeah, then I applied the linearity condition of transformation, then I observed that TW should be a zero vector.
Yeah, that is the way, that is a correct way to do it.
Okay, sir. So this part is clear. The third option goes in the similar fashion. Now, how to solve the second option? I did it in a way, just provide. You can see it in a brute force way. I proved that it is linearly independent and then concluded in that. But it's a very lengthy thing.
No. Okay, let me do it. It's not lengthy. Okay, so. So it's given that okay, so question number option 2, right?
Yes, sir.
Okay. So maybe it's okay. I'm taking back my statement. Maybe it's not lengthy. Okay, let me solve it. So it's saying whether this linear transformation is possible or not. Okay, so so U V 1 W 3 5 6, right?
Yes, sir.
Okay, so such that T of 210 is basically 10. T of 101, which is 01, and T of 356 is 56, right?
Okay, so I hadn't observed it in when I previously attempted it, but now it's quite visible. If it's TXY is Z is basically YZ.
Yeah.
Yeah, but in case suppose we are not able to suppose it's that's not
sorry,
that
how you can say that T of XYZ is YZ? Sorry, I didn't get your
yeah,
point.
see, the YZ coordinates are basically mapping to this. So we can have T as TXYZ as YZ, and it will satisfy all this.
But you have to prove that, right?
Why, sir? Because it is a linear transformation that we have to prove. Besides that, everything is okay, right?
Sorry, it's this is a linear transformation. That is that I agree.
Yeah. Then what else we need to prove?
Sir, can you proceed this? Let us finish this then.
So, so basically, you have to construct the linear transformation using these two, these three information.
Yes,
okay.
sir.
So basically, how you will construct it?
So what I tried is so 210.101.356 formed a basis for the domain.
Yeah, 210.101.356 is basically it's a basis.
Then I expressed any vector in the domain as a linear combination of these.
Yes.
Then I took T on both sides and formed it.
Yeah. So basically, once you have that linear transformation, then you should check one by one whether that linear expression is basically satisfying all three conditions. Right. Once the linear transformation will satisfy these three things, then yeah, basically you are done. Okay.
Yes, sir. So that is a lengthy process. So is there any other way out?
Sir, can you do that? Can you work it out?
I guess. Yeah, just a minute. So I guess that is probably the way to basically one way to say that this actually holds is basically it's a basis. Okay. So if okay, so let me. So I guess you know this theorem. So if this is a basis. Basis of W, sorry, V, and say I want a map from T, V to W. Then actually I can assign anything to the elements of Vn, and I can get a linear transformation. Okay. So this using this this thing you can extend it to a linear transformation from B to W. Okay, that is actually the property. Like once you assign some value to the or assign some value on a basis, so that will uniquely determine the linear transformation. So
yes,
so basically once you have a basis, so as you can as you have said, this is a basis. Okay.
Yes, sir.
So I can assign anything in that. So this will give me a linear transformation. Okay.
Yes.
So if instead of that, if I will assign like this, some 3, 4, this is some 5, 6, this is 0, 0. This also you can extend to a linear transformation because this is a basis. That is
So one doubt was this would never result in any type of inconsistency, whatever.
No, because you don't have any relation in between these two vectors because they are linearly independent. Okay. So in the codomain, so that's why this value will never create any problem. Okay. as you have already said, like in the question option 1, actually you have some relation, so that's why it's creating some problem. Okay, so let me tell you how actually we can solve this one. Okay, so the thing is, one way to solve, so this is given. So how we can construct the linear transformation. So T of 1 0. Okay,
T of 1 2 1 0 is 1 0.
Yeah. Yes. Zero one is okay. 0 1. Oh, yes,
So this is 1 0 1.
Yeah. I'm actually making a lot of mistake. And T of 3 5 6 5 6. Okay, what actually you can do? Okay, so okay, I'm not going to do the complete computation. So first, so to get an expression for this linear transformation, okay, what you need to know? So this XYZ is basically what? X into 1 0 0, right? Y into
correct
0 1 0 plus Z into 0 0 1. Okay. So once you apply T, what you will get? Once you apply T, you will get X into T of this,
right?
Y into T of this, and Z into T of this, right?
Correct.
So to get a algebraic expression for T of XYZ, you just need to know the values of this.
Okay.
T of 0 1 0 0 0 1 0 0 0 1.
Right. Okay.
So what is given here? These three things are given, right? This is 0 1, this is 0 1, this is
5 6.
Yeah, this is 5 6. Okay, and it is given that this 2 1 0 1 also not given, and you can check that 2 1 0 1 0 1 and 3 5 6 is a basis.
Correct.
Right. So that means you can express 1 0 0 as a linear combination of some alpha of 2 1 0, beta of 1 0 1. That you need to find alpha, beta, and gamma for this. So once you find this, then you can get T of 1 0 0, right?
Yes.
Then you substitute the value of T of 1 0 0 here. Similarly, substitute the value of T 0 0 1 0 here and 0 0 1 here. Then you will get a algebraic expression for T of XYZ, right?
Okay. Okay.
So that is the way you should do this one. Okay, so
sir, the transformation matrix, say example for we are solving for 0 1 0 and 0 0 1. So let alpha 1 beta 1 gamma 1 alpha 2 beta 2 and respectively would be there. So the transformation matrix correspondingly, I'm telling in place of columns it would be alpha 1 beta 1 gamma 1 alpha 2 beta 2.
No. Okay, so why you are talking? How you can talk about the transformation matrix, like and with respect to what basis you are taking the transformation matrix?
Yeah, sir. So, sir, transformation
matrix.
What is
when you are talking about transformation matrix, what is your basis here? Ordered basis here.
Ordered basis, yes, sir. 1 0 0 0 1 0 0 0 1.
1 0 0.
So from this step, how do we generate transformation matrix, sir?
No. I'm asking what is your order basis for the, because it's so odd here. Basis is not given. So how you can talk about the transformation matrix? There is in the whole question I never mentioned some order basis for domain and codomain.
Okay, sir. Okay.
So since you don't have anything, then how you can talk about the transformation? First, you have to fix some ordered basis. Okay, this is a basis for domain. Okay, this is also a basis for domain. Then what you will get from that? You are taking both the basis and they are basis of domain. Okay, so
luckily in this case, the three vectors which are given are independent in R3.
Yeah, okay, maybe luckily or maybe yeah. So,
but if it is not independent, we cannot use this procedure, right?
No, certainly no. Yeah. Then you have to check. So you have to see any kind of relation, or you have to try to maybe disprove it or maybe prove it. So you have to
So
check.
what will be T of 1, 0, 0?
No, that you need to find.
So I got alpha, beta, gamma. Now what will be the T equal to?
No, you know alpha, beta, gamma, right? You just you know the value of this, right? You just put it and you just do the arithmetic.
Yes, now got it.
Yeah.
Yes,
So, okay, so I guess we have almost anything from 6 point. Okay, is there anything left in the 6.1? Okay, so the next thing what I want to discuss is basically how you can okay, probably this is the last thing I'm going to discuss. After that, I will take your question. So the thing now I want to discuss how you can. I have explained you the procedure how. So T is given, and some basis is given, some beta ordered basis, obviously, and gamma, and how using this how we can construct a matrix. Okay, so now I'll tell you how you can come from here to here. Okay, so suppose a matrix is given, okay, and some ordered basis is given. Okay, so suppose a matrix is given and some ordered basis is given, how I can compute T. Okay. So suppose I have V to W. T is a linear transformation, but I don't know what the T is. And with respect to some basis, with respect to two ordered basis, one is beta, which is a basis of B, and another is which is a basis of W, and I know the matrix representation. This is my matrix. A11, A21, and I guess this is AM1, and this is A1N, this is A2N, this is AN. Okay, so the first question is how actually when we are computing the matrix representation, how actually we got this column?
So we express T of V1 as a linear combination of the basis vector of the codomain.
Yeah. So then basically by using the first column, we can know what is T of V1, right?
Correct.
Using this column, I can know what is the image of T of V1 because that is how I construct the first column. Okay. So T of V1 is basically what?
A11, W1.
Yes. And AM1,
W1.
WM. Yeah. And similarly, I can say what is T of V2 because the second column of the matrix will give me what is the value of T of V2. Okay. So then similarly, the nth column will give me the value of T of Vn, right? So then what I know? So I know T, the value of T on a basis of V, right? So once I know the linear transformation on a basis, then basically I know everything about the linear transformation, right? Because because this is how you can construct that linear transformation. If you know on a basis, then basically you can construct that linear transformation using this method, right? So what information we had in this question? We know the value of the linear transformation on a basis, right? This is a basis 2, 1, 0, 1, 0, 1, 3, 5, 6. It's a basis on R3. And once I know the linear transformation, the value of the linear transformation on the basis of the domain, then I can compute it explicitly, right? This is the procedure. So using this matrix, I can compute the values of the linear transformation on a basis, that ordered basis beta. So once I know the values of the linear transformation on each element of the basis beta, then I can compute the complete linear transformation. That is how you can. I'll do example. That is how you can come from a matrix to linear transformation.
Okay.
So again, I guess this is in 6.1. So just tell me which question I should solve in 6.1.
Sir, any example you please do.
No, like example, yes.
And,
yeah, that is what I want to do. Like I want to solve some question which from your activity part. So then it will help you in both the directions.
It's such a question is 8 and 9.
Well, I don't want to do this one in the beginning. Okay, I can do it, but yeah, because it's more or less a general thing. Okay, so let me take some example. Okay, so let me do it for say this is a linear transformation. Let me.
So please consider R3.
Okay, see, the idea is basically same. Okay, if I'll take R3, then I will do maybe some half an hour calculation. Okay, if you want me to do, then I can do that. Okay. So there is no some. Okay, maybe I should do something from R2 to R3, because every time I was doing some kind of same thing. So what will be the okay? So again, I'll take something here. Maybe say this is the basis. So maybe say 4, 5 and 1, 3. This is a basis. Okay. And so for the codomain, I'll choose the easier one. Okay.
So please don't choose standard.
Okay, so then basically I'm in the same position. I have to do a lot of computation. Okay. See, you should get the idea. Okay, so
that only will give us a clear picture.
No, if you understand this one, then certainly you should able to do for any basis. Okay,
because that directly comes XYZ.
No, as I said, the only tricky part is this one. Okay, the finding this. Okay.
Correct.
So if you know this one, then certainly you can do it. Okay, that is this concept has nothing to do with this standard basis. If you can find the linear combination, then you should able to do it. Okay. So probably in this case, I should choose here standard basis, not here. Okay. So because if I'll choose here, then certainly it won't help me much. Okay. So what will be a matrix representation of this transformation? So I am asking about the order of the matrix. So what will be the order of the matrix which represent this linear transformation T?
3 cross 2.
3 cross 2.
Right. So let me take some 3 cross 2 example. Say 3, 1, 0, Next one, maybe say 1 1 0. Maybe say 0 1 1.
3 cross 2.
Okay, sorry. Right, this is the matrix representation. Suppose this is the matrix representation of the linear transformation with respect to beta. This is a ordered basis, and with respect to gamma, this is also a ordered basis. Okay, so as I have said it earlier, see, this column will give me the image of the first element of the basis in the of the ordered basis in the domain. So what is T of 4 5?
310.
3. No, this is not 310. This is 3 times this.
Correct. So that will finally be 3.
Okay, sorry. My bad. Yeah, this is basically 310. Okay.
That is why I asked you to choose different bases.
Okay, so the thing is, if here I'll choose a different basis, then actually it's not a problem for me. Okay. So okay, okay, because here actually I have to choose a easy basis in the domain. Okay. So okay, so tell me one basis, maybe
101.
3 1 0 0 1 1. Okay, this is my matrix. Tell me now the basis.
101.
101.
And 110.
110.
And 111.
111. Fine. This is the basis for the codomain. Okay. So then what will be the image? So now what will be the image of 4 5 under this linear transformation? This is basically 3. So this is 3 times the first element of the basis, which is 1 0 1. Okay, the sound is coming from me or
kind of a noise.
So then T of 4 5 is 3 times this one. Then I have to take the second column of the second entry of this first column, 1 into 1 1 0, 0 into 1 1 1, which is same as
413.
4
1 3.
1 3. Okay, so this is T of 4 5. The next one is T of 1 3, right?
Yeah.
So what is T of 1 3 then? 0
110.
0 into 1 0 1, right?
Yeah.
Then this one, second entry of the second column is 1 into 1 1 0, then 1 into 1 1 1. So this is
2 2 2 1.
2 2 1 2 2 1. So what I have now, so basically what I know now, I know that T is a linear transformation from R2 to R2, and T of 4 5 is 4 1 3, and T of 1 3 is 2 2 1, right? This is what I got from the matrix representation. Okay, I want an algebraic expression for this linear transformation. Right? So this is basically x times 1 0 plus y times 0 1, right?
Yeah. Okay.
So the next thing what I have to do, I know these things. T of 4 5 I know, T of 1 3 I don't know what is T of 1 0, but I can get T of 1 0 from these two things, right? So first, for that, what I have to do, I have to write 1 0 as a linear combination of 4, 5 and 1, 3, right? So from here, what you will get?
So you mean to say every time these two vectors which you given will be always independent?
No, if it is not independent, then certainly, so no, this is a basis, the ordered basis is given. So if it's a basis, then certainly it's a independent. And if you don't know the linear transformation on a basis, then actually you cannot compute the linear transformation. There can be infinitely many linear transformation. Okay. So that's why if you know the basis, then you will get a unique linear transformation. Okay.
Right.
Okay. So from here, what I can get, so what this thing will give me 4 alpha plus beta is 1.
5 alpha plus 3 beta is 0.
5 alpha
plus 3
beta is 0. So if I solve, then what I will get? So this is 12 alpha minus 5 alpha. It's basically 7 alpha, which
alpha
is
equal to 3 by 7.
3. That means alpha is 3 by 7. So once alpha I know. So what is so there? Okay. So alpha is 3 by 7. Then beta is 1 minus
12 by 7.
12 by 7 minus 5 by 7.
Minus 5 by 7.
Okay. So let me do it. New page. Okay. So let me do it explicitly. So then what is the image of T of 1, 0? It's alpha 3, 7 times T of 4, 5. Right?
Yes.
Minus 5 by 7 into T of 1, 3. So what is T of 4, 5? This is 4, 1, 3, right?
4, 1, 3.
What is T of 1, 3? 2, 2, 1. So now you know, okay, so you will get some number, okay, ABC. Okay, I don't want to compute this. Okay. You do the calculation, okay, you will get something. Okay, so I know the value of T of 1, 0, right? That is, I say it's ABC. Okay. Okay, if you want, you can compute and tell me. Okay, so so the next thing what I need to compute, I need to compute T of, okay, it's a mistake, T of 0, 1, right?
Yeah.
So I want to express 0, 1 as a linear combination of say 4, 5
and
1, 3. So this will give me 4 alpha plus beta is 0.
Equal to 0.
Then 5 alpha plus 3 beta is 1, right? So then we multiply 3.
The alpha is minus 1 by 7.
Then beta is minus 4 plus 4 by 7, right? If alpha is minus 1 by 7, then if you
yes,
so then this is minus 1 by 7, 4, 5, 4 by 7, 1, 3. So I can compute the value of this, which is what? Minus 1 by 7 into T of 4, 5, which is 4, 1, 3. Then 4 by 7 into T of 1, 3, which is 2, 2, 1. Say this is ABCD, may say this is EFG. So I know, now I know T of 0, 1 and T of 1, 0. So then I'm done, right? This is X into T of 1, 0 y into t of 0, 1. And I know the value of t of 1, 0. This is basically a, b, c. And I know the value of 0, 1, which is e, f, g. So then I get the map. I get t. Right? Clear?
Yes. Yes.
Okay.
Yes.
Okay, I guess I'll not discuss any concept.
Sir, can you please provide a proof of question number 10, option 1?
Please, we can. Okay, so I guess linear transformation is, I guess Susmita explained it properly. Okay, who is RT?
The inverse was not explained.
Sorry?
Inverse wasn't there in her.
Actually, inverse, okay. Inverse, actually, there is, I guess, one question in inverse, right?
Yes, sir. Option 1 only. I want to prove. Can you provide it?
So basically, it's that if t is linear, then you have to show that t inverse is linear, right? So I guess that is what you are asking, right?
It is one.
Yes,
Is
sir,
it
yes, sir.
true only if it is isomorphism?
Only if it is isomorphism, then that inverse will exist.
Yeah, see, it's like a function. Okay. Hello.
So, sir, can you give a generic proof of that?
Sorry, you want the proof? Okay, like you can.
Yes, sir.
Okay, like Susmita is saying something like I'll post the discourse link where the proof had been written. Okay, it's just some thing you need to check. Actually, it's not a big thing to do.
Okay, ma'am.
Okay, so any other doubt in 6.1? Hello?
No, sir.
Question number 9.
Question number 9. Yeah, so what, okay, so before that, how you solved question number 8?
Yeah, I solved that, sir.
Yeah, so what is your
But
answer?
question number 9, I couldn't do.
Yeah, so what is your answer
For
in
question,
that?
for question 9, sir.
Yes.
No, sir, I couldn't solve it.
No, I'm saying what question number 8, because question number, if I have to solve question number 9, then I have to solve question number 8. Okay, provide.
Yeah, so for question number 8, the correct option is C.
That is fine, but how you solved it? That is correct option is C, that I know. But how you solved it?
Yeah, sir, just that as you explained, we'll take beta and gamma. In 8th option, we'll take beta and gamma as the standard basis.
Let beta and gamma be two bases of R square. Okay. So
yeah, and both are the standard basis.
And A, B, C, D is the matrix representation of the linear transformation R square with respect to beta for the domain and for the codomain.
Standard basis for both sides.
Yeah. So T is from R square to R square. And AB, CD is the matrix representation of the linear transformation with respect to beta, which is the standard basis for the domain as well as for the codomain, right?
Yes, sir.
Yeah. So then what is T?
So from this, T is given to be AC and BD. So we can say that T of 1, 0 is AC.
AC. I have,
So you
yeah.
matrix should be A.
Correct. It should be AC,
Yeah.
BD.
So T of 10 is AC.
Fine. Okay.
Yes,
So then what is T of 01?
01 is BD.
BD, right? So then what
Yes,
will
sir.
be your linear transformation? What is then how you compute T of XY? It's basically X into
AC we can write as A times 1 comma 0 and
right?
yeah.
This is X into A comma C plus Y into B comma D, right?
Yes, sir.
So this is AX plus BY CX plus DY. So this is my map. Okay. So then what I have to do, I have to find the matrix representation of the linear transformation in the question number 8. Okay. New page after. Okay. So with respect to beta,
you have to interchange the
yeah. So okay. So I guess now I can. So this is my linear transformation. Okay. So your question is, so your question is what is the matrix representation of T with respect to gamma for both domain and codomain, right?
Yes.
Yes, sir.
So what is gamma here? Gamma is what is gamma?
1 1 and 1 minus 1.
Right. This is your gamma. This is a basis, ordered basis for both domain, codomain, right? So you'll do the same thing, right? You take T of 1 1. What is T of 1 1? Hello.
A plus B, A plus B and C plus D.
C plus D, right?
Yeah.
So then how you can, so you need to get the matrix, you need to write it as a linear combination of, to get the first column of the matrix, to be more precise. To get the first column of the matrix, you need to write this as linear combination of, since this is also we are considering gamma also as a basis of codomain, so we need to write this as a linear combination of 1 1 and 1 minus 1. So this is 1 1 and 1 minus 1. So then what will be the value of alpha beta? Alpha plus beta, alpha minus beta. Alpha plus beta is A plus B. Alpha minus beta is
C plus D.
C plus D. So now can you get the value of alpha and beta?
Yes, sir. Yes, sir.
So whatever value you will get, so what you will get here, A plus B plus C plus D by 2, right?
Yes, sir.
So then this A11 entry is basically what? A plus B plus C plus D by 2. Then what will the value of beta here? I guess, okay, you
A plus B minus C minus D.
A plus B minus C minus D by 2. Oh. Similarly, you can compute the second column, right?
Yes, sir. Yes, sir.
Yeah, so
I can do
the
that.
same procedure. Yeah. Okay, so any other question? Hello.
So I have a doubt about a question itself. So that is activity 6.2, question number 6. The first option says that there exists a linear transformation whose range is
Sorry,
contained.
6.2, question number 6, right?
Yes, sir.
Yeah.
There exists a linear transformation so that its ranges in this contained in the circle x square plus y square equals 1. So by this we mean the area bounded by the circle, or
No.
on the circle?
By means the image is content in the circle. That's all.
That means the circumference, right?
Yeah.
Okay, sir. Okay, sir.
It's basically here. So this is your set.
Okay, sir.
This is your set. Okay.
Inside the circle, right?
No. This x square plus y square equal to 1. This represent the boundary of the circle. Yeah, basically this one line. This.
So we don't put it on the circle. It's contained in the circle.
Yes, so the circle is x square plus y square equals 1, and the range is in that circle. So the range is a subset of that all set of values which satisfy the equation x square plus y square equals 1.
Just for okay. So just give me a break for 1 minute actually. Okay.
Yeah, so what is the question?
Question number 6 of activity 6.2.
So yeah, the image is contained in the circle. What is the question after that? Like, what is the doubt?
So we're just discussing the question whether it should be inside the circle or it is on the circle circumference.
Okay, irrespective of both the cases, do you think you can find a linear transformation satisfying that?
Ma'am, if it is the area bounded by the circle, then we can, right?
I think in both cases we can.
How?
The zero subspace.
Yeah. Actually, they can take the zero map. Yeah.
Zero map.
Yeah. No,
So
like in this case, content in the circle means So we are taking the boundary of the circle. Okay.
Then zero will not be existing.
No. So if I'll write like this, x square plus y square is less than or equal to 1, then actually, so 0 is included. Okay. So this is a set, right? So what do you mean by that? The range is content in the circle. So this is a set, right? So this set represent the boundary of the circle, right? So that means the image content in S. If instead of that, if I'll add one more condition that there exists a non-zero linear transformation which is contained in this set, so then this statement is not correct. Okay. So if I'll just add one more condition that there exists a non-zero linear transformation whose range is content in this set.
So how can we say that?
Because if it is non-zero, then you have a line in the image, right? Image is a subspace.
Yes, sir. So the very fact that a linear transformation satisfies linearity means that the subspace has to be a line, right?
At least it certainly it can be more than line. Like it can be whole
it can
plane.
be a plane.
Yeah.
It can be, but it can be a point which is the zero, or a line, or then
So
higher
yes.
dimension.
So either it's zero or a line. If the map is from R square to R square.
Yes, sir.
Or it's a plane. Okay. So by saying that that T is non-zero, okay, I'm excluding this case, right?
Yes, sir.
So either I'll get a line or I'll get a plane. In both the cases, it cannot contain. So this circle cannot contain the line and as well as the plane, right?
Yes, sir.
Yeah.
Sir, I am not getting it. It is written T such that R square is equal to R square. That means it's a subspace. So zero vector should be there.
Yes, yes, true.
So why it is not a linear transformation?
Which one is not a linear transformation?
This only x square plus y square equal to 1.
No, what is your question? So you are saying this is a linear transformation or what?
Sir, I'm not understanding the crux of this question. What is it trying to say?
No, it's
Option
basically
1.
It's asking whether you have a linear transformation whose range is contained in the circle x square plus y square equal to 1. Whether there exists a linear transformation, asking whether there exists a linear transformation from R square to R square such that the image of T is contained inside this set, this x comma y, such that x square plus y square is 1. This is not possible, right? Because 0 comma 0 is in image of T, right? But
Right.
0 comma 0 is not in S, right?
Correct.
Yeah. So then you cannot you cannot construct one example which satisfy this condition, right? So
Yes. Okay.
Okay. So any other doubt?
So can you give me the analogy for kernel topic? So
Sorry?
kernel topic, sir. Can you give me the analogy for that? So what is that?
Kernel, okay. No, any other question from activity like
No, sir.
okay, so then,
Not done the activity, so no please.
okay, so yeah. So it's kernel is basically it's a definition, like kernel of
I think there is a question number 7 also you can.
T is it's a linear transformation from V to W. Then kernel of T is by definition the element of V such that T of V is 0. So it's basically set of all elements of V that maps to the 0 vector of W. Okay. So clearly this is a subset of V, right? But yeah, just like image of T, this is also a subspace of kernel of T is a subspace of V. Okay. And T is 1, 1 if and only kernel of T is only 0 vector. The kernel of T contains only the 0 vector. Yeah. So
the definition part is okay, but can you give me the analogy of kernel with functions, like image is equivalent to range of the function?
What do you mean by analogy? Like I'm not getting.
Sir, like image of V, we can say the image of V is like range of the function, right?
It's depend on the function. Yeah. So image of T can be image of T is basically the range of the function. Yeah. So
yeah. So in that way only I'm saying that can we say kernel
If there are many pre-images for a 0,
No,
0
image and sorry.
If there are many pre-images for the 0 in the image.
Yeah, that is basically the definition of the kernel, right?
Yeah.
You are basically searching all the elements which that maps to the 0 vector in W. Okay, but yeah, I still I didn't understand. Like, see, image of T and range of T, they are basically the same thing but different name. We are just giving some different name, but they are basically the same, right?
Correct. So that way only I'm saying that I'm not able to understand the kernel word. So can I get similar word to that kernel? So that way I can understand easily. Or you can give me the example. So there is one example, equity question 6.2, 7th question. So please explain that question.
Yeah. So what? Okay. So. Okay, one thing is, okay, by knowing that range and image word are both are same, so how actually it's helping you to understand the concept?
Actually, sir, I know range concept very well, so I can relate image word to that.
Okay, certainly I'm writing 0 and I am writing 0. So then how it will help me to understand what is I am writing, like. So image of T and range of T, they are basically the same thing. Image of T and range of T. This is 0 and this is 0. That is the difference. There is no difference between this and this.
Sir.
Yeah. So still I don't know how it will help you to understand them, because similarly
The only difference there is that
this.
So the only difference is that the things for subsets and images for subspace, right? So that way.
Okay, so in this case, for a linear transformation, basically they are both are same and they are subspace. Okay. So let me define. So this is my map, right? So what is so just tell me what is the definition of kernel of T?
So that only I'm not able to understand. No, that's why I asked to explain this question.
Okay. So I am asking you the definition. You told me, na, you know the definition.
Yeah, sir. In my knowledge, I understood that the fact that
no, you tell me the definition. I wrote the definition. Okay, just now I wrote the definition and you told me that you know the definition. Okay, just tell me what is the
if the kernel of T is the subspace of V.
Subspace of V. So what is V?
Yes, R square.
Yeah. So what is W here? This is also R square. So what is kernel of T? It's basically
subspace of R square.
0y
x comma R square, such that
x is equal to 0.
X equal to 0, right?
Okay. Yes.
Okay, sir.
This is kernel, right?
Correct.
So if zero zero, then so what is T of xy?
X comma 0.
This is 0 0, right?
Correct.
That implies
X is 0.
X is 0, right? If T of x comma y is 0 0, that means x is 0, right?
Right.
So from here you can say that kernel of T is a subset of this set, right?
Right.
Because what I am saying, if T of x comma y is 0, 0, this implies the x coordinate is 0. Okay, so then basically I am saying if xy is so this basically says if xy is in the kernel of T, that means my x coordinate is 0. Okay, so which is same as kernel of T is a subset of this, right?
Yes.
So now if you compute T of 0y, what is T of 0y?
0, 0.
0, 0. That means 0y is in kernel of T, right?
Right.
T of 0y is 0, 0. That means 0y is kernel of T for all y in R, right? So that means 0 comma y, where y is in R, it is a subset of kernel of T, right?
Yes, sir.
So from these two things, what you can say?
0 comma y and 0 comma scroll up, please.
I'm saying from these two things, what you can say about the kernel of T. You don't have to look
Kernel of T is
the
same,
above things. Kernel of, so basically from here I showed that kernel of T is a subset of this. Okay. And here I showed that this set is a subset of kernel of T. So this basically using
Both are
this,
same.
I can say that, see, if A is a subset of B and B is a subset of A, that means A is equals to B, right? So then I can say that kernel of T is nothing but this set, right? So solving, so finding kernel is basically is equivalent to solving a system of linear equations. Okay. So what I'm basically here I'm doing, I'm just, so when I'm comparing this with 0, 0, then I actually I'm getting a system of linear equation 0, 0, x equal to 0 and 0 equal to 0. Okay. Right? Is it clear like how actually here we got the kernel of the linear transformation?
Yes.
Yeah. So similarly, you have to do it. Like, see, in the upcoming lectures, maybe in upcoming week, you will see you will learn some theorems like how to find. Maybe in okay, see, in actually in week in lecture 3, have you watched week 6 lecture 3? Hello, am I audible?
Yes, sir, you are audible.
Okay, maybe she has problem with her network. Maybe. Okay, so fine. Okay, any other doubt?
Sir, could you please look into the office query list and see if we can have an office hour session, because I have two conceptual doubts and I think it will take some time.
Okay, just a minute. So, basis of a kernel. I could not understand the link between null space and kernel and that between image and kernel space as explained as explained by the professor in lecture 6. So okay, so you want the proof, right?
Not the proof. For the question which you read out, I didn't understand what he was doing. Couldn't catch at all. And then regarding the basis of kernel, my doubt was uh, when we are taking different basis vectors, not the standard basis, why is the need arising to express the basis of null space as a linear combination of the basis of the domain in order to derive the basis for kernel?
Yeah, so that is what the matrix do, right? The matrix give you the coordinate vector. So okay, so what this?
Yeah. So I want this to be illustrated.
Okay, so okay, like before that, I just want to ask you one question. So,
yes, sir.
So suppose you have a linear map, right?
Yes, sir.
And you have a basis here.
Yes, sir.
And this is a basis here. Okay, and with respect to this basis, you have a matrix, right?
Yes, sir.
So my question is, what this thing will tell you?
So B will be my images, and X is the basis.
That X is not a basis. X is a okay. So let's say, let me say it's a map from R3 to R3, right? So X is a vector in R3, right?
Yes, sir.
And so then obviously B is also a vector in R3, right?
Yes, sir.
So my question is, what actually this, when I'm multiplying AX times B, so this is not an arbitrary matrix A, right? A is not an arbitrary matrix. It's a matrix
Yes,
representation of representation of P with respect to this basis.
Yes, sir.
So so when I'm multiplying this AX, so B has a basis, say B1.
So,
yeah.
The dimension of E is M cross N.
It's a 3 cross 3 matrix. Let's
okay.
stick to the
Okay, give an example. Okay.
Yeah.
So 3 cross 3, and then X should be 1 cross 3, right?
Yes. X is basically 3 cross 3 cross 1.
So 1 cross 3.
1
because
cross 3.
the column gets multiplied, right?
Okay, this is 1 cross 3. If it is a column.
Okay, so X is something like this. Okay, ABC. This is 3 cross 1, right?
But sir, this is not how we define A, right? We define the columns and then multiply it to W to get the image.
What, you multiply column?
Yes, sir. Column to the respective WIs, and then we get TVI.
So actually it is XA equal to B, right?
Yes, sir. Yes, sir. That's what I'm trying.
No. Okay, so that is okay. That is fine. Like, but what I'm saying, okay, so that is you can. So that is basically you are just writing. Okay. So leave that part. My question is what this thing will tell.
So I can see it see that in only that way. This way I can't figure out what it is.
Okay, so the thing is, what actually this particular thing will tell you. So suppose so this is a ordered basis, right? And
yes, sir.
This is a ordered basis. Okay.
Yes, sir.
So so this ABC, suppose this is EFG.
Yes, sir.
Right. So So what is actually we are so what actually this thing will tell you? It's basically so using A, B, C, you can form a element in your vector space R3. So V. So how you will get a element? So A V1, B V2 plus C V3, right?
So it will be alpha 1, right?
Sorry?
Oh, sorry. Okay.
No, ABC are real numbers, right? Okay. So this is a vector in R3, right?
Yes, sir.
So if you apply this, you will get some element in your codomain, which is also R3.
Yes, sir.
So this thing is basically giving you the coordinates vector of this one. This is
Yes,
not. This is nothing but E gamma 1 F gamma 2 G gamma 3, right?
Yes, sir.
So okay, so let me tell you one. Okay, this part is clear. It's basically it's giving you the coordinate vector. Okay, fine. So so now you can see what actually this X, and so by multiplying X, what actually you are getting. This part is clear, right?
Sir, this A is not the transformation matrix, right?
Which one?
What is this A?
A is basically the transformation matrix with respect to this beta and gamma.
Sir, in that case, X must be gamma, right?
What?
X must be expressed in is gamma, correct?
X must be gamma. X is any arbitrary element of.
Sir, can you go back to any example which we did and then say what is AX and we are?
Okay, so just give me a minute. Say T of xy is 2x 2y, right?
Yes, sir.
Say one basis, some basis, some maybe say this one is what 1 1 1 3. Okay, this one is 0 1. Sorry, 1 0 0 1. So what will be the matrix of this one? What will be the matrix of this one?
Sir, 2 2 first column.
Next one is 2
6. Yes, sir.
So okay, so I multiply this one, maybe say with 1 1, right?
Okay, sir.
What I will get? Four, right? This one is 4.
Yes,
this one
sir.
is 8, right?
Yes, sir.
So so this is a coordinate vector of some vector in R square. So what I will do, I'll take this one, this 1 into 1 1, right? Then again I will take 1 and multiply with this one 1 3. What I will get?
2 4.
2 4, right?
Yes, sir.
What is T of 2 4?
It's 4,8.
4,8, right?
Yes, sir.
So basically, this one will give me the coordinate vector of this one with respect to this basis. So this is nothing but 4 times 1, 0 plus 8 times 0, 1. Right?
Yes, sir.
So now is it clear, like what I was trying to say here?
Yes, sir. Yes, sir. Yes, sir. Yes,
So
sir.
when you are multiplying some vector, so basically using this vector, okay, you can construct a vector in the domain, right? Using this basis, which is precisely this one. Okay. And when you apply T on this element, so you will get a vector in the codomain. Okay. And this EFG will give you the coordinate vector of this vector with respect to the basis of the codomain. Clear, right?
Yes, sir.
So now can you see, like so okay, now I guess that is the part I guess you missed in that proof. Okay, so I'll suggest you to go and check it. Otherwise, okay, like I'll discuss with Subhajit whether when he's planning to take a session. Otherwise, we can sort. I guess we can sort it out in discourse. Okay.
This is answer to which proof? Which question?
Probably your first question. So basically, sir was giving some proof, right? How actually you are.
Yeah. So the column space and image and row space and kernel.
Yeah. So okay. So let me quickly tell you something. So so this matrix. So why the kernel's null space? So this is your matrix, right?
Yes, sir.
So let me tell you only about the null space. Then you try to think for the same for the range also. Okay.
Yes, sir.
So suppose 1, 1. So T is a so again I'll stick to R3. So V is R3 and V1, V2, V3 is a basis. This is say
Sir, probably the null space one was clear. Yes, sir. The null space one I got, I understood, but the column space, that thing I didn't understand. Null space, I understood that we get the linear combination, which we get the unique linear combination will also be in the be an element of the null space. That thing I understood.
No. I guess whatever you are saying is not correct. Okay, so the thing is okay. So what? Okay, let me complete it. What I was trying to say, but maybe whatever you said is correct. But I guess yeah. So let me complete what I'm trying to say. Okay,
sir.
so so okay. So you can only understand the thing what I'm going to tell if you have understood this one properly. Okay. So
Yes, sir.
so. Okay, so this is your matrix A, right?
Yes, sir.
So you have a null space. Suppose ABC, which is a non-zero vector, but this is in the null space of A. That means what? A, B, C, 0, 0, 0, right? So then I can say that by the previous argument, whatever I was trying to say here, AB1, so ABC is not equal to 0, 0, right? That means
Yes, sir.
AB1, AB2, AB3 is not 0, right? Sorry. ABC.
Yes, sir. Yes, sir. No, it's
this is not 0.
Yes, sir.
But so let's say this is B. So what? But now what is T of B? Now what is T of B?
So it will
Is it
be
0, 0,
literally
0?
T of
This is, see, that is what I'm saying. This one will give you the coordinate of the image of T of B. Okay.
So it is 0, 0, 0.
0, 0, 0. So what is the, so this is what? T of B is basically what? 0 times
W1, 0 times W2, 0 times W3.
Which is 0, right?
Yes, sir.
So basically that is the thing actually he is doing. So once you have a null space, okay, so you can create element, okay, such that the image of the element is 0.
Got
right?
it.
Yeah. So similarly, actually, he is doing the same thing for the column space. Okay. You try to okay. So if, as I said, if you have, so the main idea he is using in that proof is basically this one. See, this matrix transfer one coordinate vector to another coordinate vector. Okay. So
Yes,
this is what he is using. But still, if it is not clear, just let me know. Like I can write it out completely, and I can give it. Okay.
Okay, sir.
Okay, so it's not issue. Otherwise, yeah. So if, I'll ask Subhajit whether he's planning to when he's planning to conduct this office hour session, then we can discuss it there completely. Okay.
Okay.
And if it is not going to happen, then just remind me in discourse. Then definitely I'll give you the complete proof. Actually, how he's doing there. Okay.
Okay. Thank you, sir.
Okay. Yeah. Okay. So then I'll stop now. Yeah.
Thank you.
Yeah. Thanks. To all.
Hello.
Yeah. Hello.
One question here, sir.
Huh.
So I have been through statistics and mathematics courses, these those sessions that we have for around 2.5 hours. So in statistics, what I see is that they use slides and one portal where they put questions and we solve it, and then they provide the solution. But in mathematics, we do not follow that approach, right?
Sorry. Actually, I don't know what sort of thing they follow in statistics. So different course has different structure. So
but it's part of same course, right?
I think, are they using peer desk? Something like that.
Yes.
Sorry?
So, they are using peer desk and asking them to post solutions and then.
No, I guess we are not planning to do peer text because so the thing is, one of the disadvantage of peer deck, according to me, you cannot write much. Okay, so the thing is I can give you some question and I can I can expect some answer from you, but when I have to start solving this, then I cannot do that in peer deck properly. Okay, as you can see, for a particular question you have to write a lot. Okay, so that is one of the disadvantages of peer deck.
Yeah, but this advantage of this approach in mathematics also is that when somebody goes to this video lecture after 1 week and they see the recorded session, they do not get to know when the question is starting, right? We do not get to know which question number and when that is starting, and we have to go through all 2.5 hours to
how will figure it out in peer deck, say recording session?
In YouTube, I can slide through and see when a particular slide question number or that screen appears. And I'll see that, yeah, this is after 10 minutes, there is a new question being discussed over there.
That is what you can do here, right? What sort of question I'm solving, and so you can do even with the solve with us because we are preparing questions, right? So if you keep on moving, then you can see which question actually he is discussing. So I don't see any difference. Particularly, this is an open session, so forget about that. I'm talking about the solve with session. So in the solve with session, we are writing questions, right? each and every time we are writing question and after that we are solving. So if you keep on moving, then you can see, right, which question actually at that particular time, which question the instructor is discussing. Because
if I see the screen right now, I do not know which question number we are.
No. This is I'm not doing the solve with us session now. When I'm doing the solve with session, in the solve with session, we prepare some questions, right?
Okay.
We type some question in that PDF and we solve them, right? So you can do the same thing, right?
I'll try once more.
Yeah,
to
you
follow
check
this
the
approach.
solve with
Yes.
session. Yeah.
Sure. I'll try that.
See, the thing is, okay. So the thing is, I'm not saying that this whatever peer deck is not a good thing, but the problem. Okay, so what
I agree, sir. I agree.
Problem is I cannot write much. Okay, with the peer deck. Okay,
Agreed.
I don't have. So when I have to explain something, I have to explain everything in the mouth. Okay.
Correct.
Or maybe whatever. So I cannot write some 20 pages in a slide, right? So so then I have to skip a lot of things. Okay. Then I cannot express it in that session. Okay. So when you don't have to write much, okay, in that case you can use peer deck and you can take session. But when you have to write a lot of things, then see, if someone will tell me to write all these things in peer deck, then it will take a lot of time. Okay, so
right. So I tried in while I was preparing for the quiz one, I had very less time, and I just went through solve with the sessions of statistics, and then when I switched to mathematics, it was completely different because I do not attend the sessions every time live. So
the thing is, you can only get that features in solve with a session. If you go and check for the open session, then certainly you will not get anything, because
that's right.
By seeing this screen, you cannot figure out which question actually I am discussing. Okay, that's only you can do in solve with a session, probably tomorrow session. Okay, so
yeah, I will try to keep up. I will try to change myself according to that. I'll try again.
Yeah. So my point is, okay, so someone already asked in discourse that why you are not taking this what peer deck in maths. Okay, so
every teacher has their own approach. That I agree on that also.
Thing is, okay, so the thing is, what is my point is, like, you cannot write much in peer deck, then you have to tell a lot of things in your mouth
verbally. Okay. Yes.
Yeah, so then yeah, so then obviously, like, you will face problem. Okay, so that is the thing. So here actually I can write whatever I want to write. Okay, so there I can do the same thing. Okay, so
I was just looking for an approach where I can minimize my time to go through the lecture and just focus on particular question. I solve.
I understand. Yes. Going through this open session is really painful. Okay, so yeah, so because you don't know what actually at a particular point of time what I am discussing. But if you go through the solve with us session, then actually you can figure out what question actually at that particular time, what question that instructor is discussing. Okay, that is possible with solve with us. Okay.
I will try my way, another way, but I just made my point so that in future,
I got
somebody, in future they may take it as a standard approach for all the subjects. Otherwise, every teacher has their own approach, and the students has to match their frequency according to that.
Yeah.
Thank you very much, sir.
Thank you. Thank